For decades, the oceans have guarded many Cold War secrets beneath their surface. Soviet nuclear submarines that sank with their crews and never returned home. These steel giants are scattered across the world's seabeds, from the North Atlantic to the icy waters of the Arctic, acting as silent tombs whose contents have remained hidden for generations. Subscribe and hit the bell so you don't miss any of our videos about submarine secrets, Cold War mysteries, and shocking discoveries in the oceans. The story of sunk submarines is not new. We know that several Soviet nuclear vessels were lost on missions, in accidents, or due to technical failures between the years 1960 and 1980. Many of these submersibles carried weapons, nuclear reactors, and tons of radioactive fuel. For decades, experts assumed that, under thousands of meters of water, corrosion and deep pressure would simply seal those threats forever. It was an assumption based on logic. The depths were too extreme for radiation to easily escape, and the slow oxidation of these structures would keep them contained. But that logic has just been called into question. Recently, international teams of marine scientists and underwater robotics experts began using remotely operated vehicles, ROVs, to accurately film and scan the wreckage of several lost Soviet submarines. Equipped with high-definition cameras, radiation sensors, and 3D scanners capable of mapping structures under extreme ocean pressure, these robots allowed a real approach for the first time that does not rely on human divers, something impossible at those depths. What the ROVs captured was not simply images of corroded hulls, it was direct evidence that things are happening inside these steel tombs that modern science is only just beginning to understand. When one of the robots approached the hull of a submerged submarine, the camera revealed unevenly corroded internal walls, structural holes, and areas where water pressure had completely deformed the metal. In some internal compartments, the robot found structures that appeared unnaturally twisted, as if they had been subjected not only to pressure, but to internal explosions, segmented collapses, or containment failures. Measurement teams detected radiation levels inconsistent with what was expected. These were not huge leaks, nor areas with instantly lethal radiation, but measurable increases compared to the seabed background level. These increases were localized at specific points inside and around the nuclear reactor compartments and fuel storage areas. While the meters did not reach levels that pose an immediate catastrophe on the surface, they did show that the deterioration of these structures is active and progressive. Worse still, the data suggests that the most dangerous factor is not necessarily the reactor itself, which is usually shielded by several layers of steel and concrete, but the advanced corrosion of the covers, tanks, and sealed systems that have suffered decades of exposure to the extreme pressure and salinity of deep water. This corrosion could eventually allow radioactive substances and other toxic compounds to be released into the surrounding marine environment. But the most disturbing finding was neither physical nor chemical. It was structural and dynamic. The ROVs were also equipped with sensors that measured hull integrity and deformation in real time. Some of the wreckage appears to be in what engineers call a critical state of structural collapse, where small failures can cause major ruptures without the need for an external event. This means that a sudden hull collapse could occur without warning, releasing materials contained for decades. These observations led to a terrifying question. What happens if one of these reactors or other pressurized systems not only corrodes, but suddenly collapses, releasing its contents into the ocean? And furthermore, what consequences would these releases have for marine ecosystems and, eventually, for human coastlines? To understand why this is a real concern, and not simply an alarmist theory, one must consider how these submarines work. The nuclear reactors of the Cold War Soviet submersibles were designed to operate in a completely closed and sealed manner, with multi-centimeter steel shields and multiple layers of protection. In addition, the containment systems were redundant to prevent any leakage in the event of an emergency or external damage. However, after decades under thousands of meters of water, those layers have been exposed to relentless corrosion, constant pressure, and the chemical action of salt water. Although the primary shielding of the reactors remains relatively intact, the secondary systems, conduits, fuel tanks, and auxiliary compartments show significant degradation that could compromise the integrity of the hull in the not-too-distant future. The data recorded by the robots show that in certain areas, corrosion has advanced so much that the metal has become almost brittle, susceptible to breaking with little more than the natural pressure of deep water. When engineers modeled the progression of this damage, they realized that there is not only a risk of localized radioactive leaks, but also a possible sudden release of energy or materials if the structure abruptly collapses. This leads us to a worrying conclusion. The danger is not static, but dynamic and increasing. As the decades pass, water pressure and corrosion continue their silent work, degrading the steel casing that keeps these underwater nuclear weapons sealed. While there is no evidence that any of these submarines are about to explode in the traditional sense, there are indications that parts of their structure could fail unexpectedly. And that's not all. Comment submarine if you believe that the sunken nuclear remains represent a real risk and should be monitored urgently. The robots also captured anomalies in the magnetic fields around the reactors and compartments that are not explained solely by radiation or the presence of corroded heavy metals. These anomalies suggest that complex physical processes are occurring within these shipwrecks, possibly related to chemical reactions between seawater and the reactor or fuel materials. Although scientists do not yet have a definitive explanation for these patterns, they know they are not signs of something stable. Worse still, some sensor readings indicate the possible presence of organic and inorganic compounds that were not expected in that context, suggesting that internal degradation processes could be producing byproducts that alter the chemistry of the water around the remains. All of this points to the sunken Soviet nuclear submarines no longer being forgotten problems at the bottom of the sea. They are active structures in the process of transformation, with risks that evolve over time. The findings inside the Soviet submarine wreckage have set off alarms in the scientific community. What was once considered a historical and contained problem under the ocean is now perceived as a latent and active risk. The data obtained by the underwater robots have shown that these shipwrecks are not simple submerged monuments of the Cold War, but structures in the process of transformation with the potential to affect ecosystems and human health directly, if not properly monitored. One of the most alarming discoveries has to do with the release of radioactive material. Although the nuclear reactors remain relatively intact, the secondary containment systems, fuel tanks, and auxiliary compartments show advanced deterioration. This implies that small amounts of radiation or chemical byproducts can slowly leak into the surrounding water. In an ocean like the Arctic or the North Atlantic, even localized emissions can alter water chemistry and affect organisms that are the base of the food chain, from plankton to large fish. Oceanographic models indicate that these contaminants could slowly disperse, accumulating in specific areas of ocean currents and increasing the risk of bioaccumulation in marine species that are then consumed by mammals, birds, and eventually humans. The most worrying thing is that the degradation of the structure is a continuous process and difficult to predict, so scientists cannot estimate with certainty when or where significant leaks might occur. In addition to radiation, the sensors detected unexpected chemical byproducts derived from the interaction between saltwater and corroded metals, as well as chemical reactions within the reactor and compartments. Some of these compounds can be highly toxic to marine organisms, affecting the reproduction and survival of key species. This finding suggests that the impact of these shipwrecks could be more complex and silent than initially thought, extending for decades and affecting entire ecosystems without anyone immediately noticing. Another critical finding was the structural instability of the hull. The robots measured deformations that indicate that some sections are in a critical state, ready to collapse under minimal pressure. A sudden failure could simultaneously release multiple compounds and radioactive materials, creating what engineers call a massive release event that could alter the chemistry of large volumes of water. This does not necessarily imply a nuclear disaster like that of a terrestrial reactor, but it does imply a risk of severe localized contamination with long-range ecological consequences. These discoveries force a rethinking of the idea that the oceans are safe havens for nuclear remnants. For decades, The predominant narrative was that pressure and slow corrosion would seal the dangers forever. We now know that the risk is progressive, and that what was once considered harmless could transform into a significant environmental and health problem. Underwater robot technology was key to this breakthrough. Equipped with 4K cameras, 3D scanners, and radiation and temperature sensors, they were able to explore internal compartments impossible for humans to reach. The captured images show corroded circuits, valves, and systems with unprecedented precision, while real-time data reveals structural and chemical anomalies that challenge previous prediction models. But the findings are not just an alert. They also offer an unprecedented opportunity to study this wreckage before a major collapse occurs. The information collected allows engineers and marine biologists to understand how these materials react under decades of pressure, corrosion, and chemical changes, and to design mitigation strategies, from constant monitoring to selective containment interventions. The deeper implication is that these sunken submarines function as involuntary laboratories for extreme processes. The sensors have documented how the interaction between salt water, pressure, corroded metals, and radiation produces complex chemical and physical phenomena, which could previously only be theorized. This data can help science better predict the evolution of other underwater nuclear waste, improve safety protocols, and anticipate future risks. Globally, the discovery has implications for international policy and nuclear waste management. If a sudden collapse released significant amounts of radioactive material, even localized, the effects could be felt in the territorial waters of several countries, especially considering ocean currents and the migration of marine species. This underscores the need for cooperation between nations to monitor and manage this underwater wreckage, ensuring that the dangers do not spread inadvertently. Share this video with someone interested in naval history and the hidden dangers beneath the seas, so they can see how modern technology is revealing secrets that remained hidden for decades.